Okay, so we are going to start with something called as the forward kinematics. So forward kinematics means given joint angles, find end effector position. Now I give you a very simple example. Imagine that you have a robot which is something like this. So there are two joints. This is joint 1. This is joint 2. So forward kinematics means given these angles theta 1 and theta 2, what is the value or what is the x, y, and z position of this end effector? And the way we solve this problem is using vectors. So for my own satisfaction, I just want to write down the definition of vector. Vector has a magnitude and direction. So for an example, if I have an xy plane, this is my 0, 0. And if I say 3, 2, this is 3, 2, what that means, I need to travel 3 units in x direction and 2 units in y direction. That means if I have point O and point A, and if I draw a line and indicate that with the direction, I have a vector OA. Now, at this point, I want to clarify a few important things. To go from point O to point A, and this is common knowledge that we studied in high school. But understand, I'm gonna say that I need to go 3 units in x direction, and I'm gonna indicate that with an I. And I'm gonna indicate travel in y direction as j. I is the unit vector in one and x direction. J is the unit vector in y direction. Unit vector is the vector, and I need to write this down. Unit vector is vector with magnitude 1. So unit vector only indicates direction. So please understand, unit vector indicates direction. Now what this means is I can start from O, I can go to point B, I can start from O, I can go to point B, and from B, I can go to point A. Alternatively, I can go from O to A. Now, I want you to understand what this means. It means I can say my vector OA is equal to 3I plus 2J. The vector is 3I plus 2j. Understand, this is not a unit vector. Why this is not a unit vector? Because the magnitude of this vector from the Pythagorean theorem, the magnitude of this unit vector is equal to 3 square plus 2 square square root. This is the magnitude of this unit vector. But I can certainly find a unit vector in this direction, and I'm going to call this n hat. The unit vector in the direction OA is the vector divided by its magnitude. So if I say 3i plus 2j divided by square root of 3 square plus 2 square, now this is a unit vector. Now understand, unit vector is only going to give you direction. It does not tell you any other information. Just like I is the unit vector in x direction, j is the unit vector in y direction. If you want to go in the direction of OA, then this is the unit vector. The magnitude of this unit vector is 1. Everyone clear about unit vectors? Okay. Now, this forward kinematics is given the joints J1 and J2, we need to find out the position of the end effector. Right now, if you look at this image where I have drawn this robot has 2 arms and 2 joints. We can find out the end effector position by simple geometry. You can find sines and cosines and find where the end effector is. But real life robots are in 3 dimensions. So we are going to look at something called as the spatial kinematics. The kinematics in 3 dimensions. So for that, I need to give you the coordinate system definition. So this is the coordinate system x, y, and z. We always use right hand coordinate system. And how do you find out the right hand coordinate system? This is x, this is y, z is coming towards you. So for an example, if you look at here, this is x, this is y, and z is coming towards you. So always in robotics, we are going to use the right hand coordinate system. It may look trivial, but believe it or not, we are going to have rotations of this coordinate frame. So every time right hand coordinate system, always remember horizontal axis x, vertical axis y, and the middle finger is pointing towards z. Everyone understood this? The next thing is about the rotation. So this is positive I, positive j, positive k. So you have I, j, and k. Now what we want to do is, we want to look at the rotation. So the positive rotation is, look at your right hand, curl your fingers in the direction of rotation. If your thumb is pointing towards the positive axis, then that rotation is positive. When you studied statics and dynamics, probably you looked at counterclockwise and clockwise rotations. But please understand, now we are working in 3 dimensions. Something clockwise from here is counterclockwise from there. So do not rely on those sign conventions. Curl your fingers. Look at the direction of the thumb. If the thumb is pointing in the same direction as positive x, positive y, or positive z, then that rotation is positive. For an example, if I draw this rotation, curl your fingers in the direction of rotation. The thumb is pointing towards positive y. The rotation is positive. Curl your fingers in the direction of the rotation. Thumb is pointing towards positive z. The rotation is positive. Now curl your fingers in the direction this, and then you know that thumb is pointing towards positive x. This is positive. Everyone understood this? Oh, yeah. So this actually, let me. Like this, right? Above. Right. 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 I will let you curl your fingers. Okay. Everyone understood so far? Okay. Now here comes the tricky part. What's going to happen is these coordinate frames are going to rotate. Okay. So this is the most important section that you should remember. And I'm going to explain this multiple times. So everyone, please pay attention. You have this coordinate frame. This is, I'm going to call this x naught. I'm going to call this y naught. And I'm going to call this z naught. Okay. And then what I'm going to do is I'm going to rotate this frame about z naught by angle theta z. So this frame is rotated about z naught by theta z. So the new axis is going to be z1 because the rotation is about z. So z naught and z1 would remain as is. But this coordinate frame, which is x1 and y1, will be rotated. Everyone okay with this? This angle is going to be theta z. This angle is going to be theta z. And now what I'm going to do is I'm going to draw the projections of this x1 onto x0, x1 onto y0, y1 onto y0, and y1 onto x0. Everyone understood this? So what I have done is I have drawn these perpendiculars. So x1, the projection of x1 is on x0, projection of y1 is on y0, projection of x1 is on y0, projection of y1 is on x0. So projection of new frame onto old frame. Everyone understood this? Once again, this is extremely important. Projection of new frame onto old frame. And why this is very important? Because this gives me the rotation matrix. So I'm going to say, so remember, projection of projection on. So projection of x1, y1, z1. Projection on x0, y0, z0. Once again, this is not given in any of robotics textbooks. So everyone, please pay attention. If you And probably if you have studied projection matrices before, they basically draw projection matrices like unit vectors and find the transformation. But I want you to understand, you have your initial coordinate frame x0 and y0. You applied a rotation about z. So z0 and z1, they are aligned. You applied the rotation, which means x0 went to x1, y0 went to y1. And I want to find out the rotation matrix between x1, y1, z1 and x0, y0, z0. So think about projection of x1 on x0. Remember, this is a unit vector. So do you agree with me that this is cosine theta? So this is cosine theta z. So I'm going to say cosine theta z is equal to c theta z. Do you agree with me? Projection of x1 on y0, this guy is sine theta z. Do you agree with me? Projection of y1 onto x0, and I want you to pay attention here. This is going to be again sine theta z, but please understand it is going in the negative direction. So this is basically minus sine theta z. And the projection of y1 is cosine theta z. Now please note this term is negative. Why this term is negative? Because whenever you find the projection, you have to look at the direction of the arrow. This arrow is going towards this direction, towards left, which is in the negative direction of positive x0. So this sine theta z has to be negative. Everyone clear about the projection? Now our rotate. This is the most important relationship in entire forward kinematics, because we are going to use this again and again and again and again. So projection of x1 onto x0 is cosine theta z. Projection of x1 onto y0 is what? Sine theta z. Projection of y1 into x0, y1 into x0 is minus sine theta z. Projection of y1 into y0 is cosine theta z. Projection of x1 onto z0, 0. Projection of y1 onto z0, 0. Projection of z1 onto x0, 0. Projection of z1 onto y0 is 0. Projection of z1 onto z0, 1. That's your rotation matrix. I'm going to explain this one more time, because this is the only rotation matrix that you have to remember. And we should be able to solve any forward kinematics problem. Rotation matrices, there are multiple ways of solving forward kinematics problem. In this class, I'm going to use rotation matrices. The other classic technique to solve forward kinematics is using DH parameter. That is universally taught. But DH parameter has limitations. There are some configurations of robot where you cannot use DH parameters. But rotation matrices will always work, no matter what type of robot it is. Whether it's an articulated robot, whether it's a ground robot, whether it's a UAV, aerial robot, quadcopter, rotation matrix always works. So rotation matrix is the technique of choice, and I want you to understand this. I have two coordinate frames. The first coordinate frame is x0, y0, z0. I'm gonna rotate this coordinate frame, which means x0 will go to x1, y0 will go to y1, but z0 and z1 will be aligned because the rotation is about z. Now what I want to do is, I want to draw the projections. So to find projections, draw horizontal and vertical lines. Please understand, x1, x2, x1, y1, z1 is the new frame. X0, Y0, Z0 is the old frame. I want to find out the projection of new frame onto old frame. New to old, new to old. So to that, I want to write this rotation matrix, and this rotation matrix horizontally, if you look at these columns, it would be projection of x1, projection of y1, projection of z1, projection on x0, projection on y0, projection on z0, projection of x1 on x0. x1 on x0 is cosine theta z. Projection of x1 on y0 is sine theta z. Projection of x1 on z0, please understand x0 and z0, x1 and z0, they are perpendicular. So 0, sine theta z, cosine theta z, 0, 0, 0, 1. This is the rotation matrix. This gives you the relationship between the old coordinate frame and the new coordinate frame. Everyone understood this? That's the only coordinate transformation you need to remember to solve all forward kinematics problems. Yes?
Because looking at it, it looks like it is in minus x naught y naught plane at the same time it is at y naught z naught plane. So it's kind of tough to visualize.
Tough to visualize. Okay. This is the frame. And basically what I'm going to do is I'm going to rotate this. So the frame is this. Rotation is this. So if you want to look at the board, okay, rotate. So now you have so this is the initial frame. Now you rotate it.
Sir, so means the sir, if you want to know the final position of the point of the end effector, the solution of this matrix would give us that.
We are not there yet. Hold your horse. You have to find the homogeneous transformation.
One can explain how the negative sign.
Yeah. So negative sign is because y1, if you look at the projection, can you see that you are going in this direction? This arrow is opposite to this arrow. That's why the negative sign. Anything else? Cosine theta minus sine theta, cosine theta. That's the only transformation you have to remember to solve any 3D kinematics problem. But for the sake of completion, I'm going to write other rotation matrices, but I don't expect you to remember it. The only thing that you should remember, rotation about V is cosine theta minus sine theta, cosine theta, 0, 0, 1, 0, 0. That's it. So, but yeah.
How does it look if we're rotating to the Y or X?
Yeah, I'm going to solve that, but I don't expect you to remember it because we don't need it. But for the sake of completion, I'm going to say rotation about Y. This is rotation about Z.
Yeah.
So now again, we start with the same. X0, Y0, Z0. And now what I'm going to do is I'm going to rotate what Y. So this will become like this. This will become x1. This will become y1. And what I need to do is I need to draw perpendiculars. And please understand, whenever you draw perpendicular, we are looking for the projection of new onto old, which means the perpendicular should be onto old. Oh, that's yeah, right. Sit. 1, 5. Theta y. So projection. So this is gonna be like, and again this is in perspective. So it may not look like this. It will look something like this. So what I'm gonna do is I'm gonna write this transformation. Projection of x1, y1, z1, x0, y0, z0, and this is the rotation matrix. And remember, this rotation matrix is always, this is the old frame, this is the new frame. So we are going from the frame number 0 to frame number 1. So projection on. So if you look at x1, so this is going to be cosine theta y. This is going to be cosine theta y. X1 onto y1 is 0. X1 onto z1, that is going to be minus sine theta y. Y1 on x0 is 0. Y1 on y0 is 1. Y1 on z0 is 0. Z1 on x0 is sine theta y. Z1 on y0 is 0. Z1 on z1 on z0 is cosine theta y. And please understand, I didn't explain this clearly in this figure, but you can actually look at these projections, and that should tell you so this is going to be cosine theta y. This is going to be sine theta y. And for the sake of completion, I would do rotation about x, but understand, even though I'm explaining this, the only rotation matrix that you should remember by heart is that rotation matrix. These rotation matrices are just for reference. Now, next thing is rotation about x. And again, you have x 0, y 0, z 0, x1, y1, z1, and again this is a perspective view, so I need to draw projections something like these. This is perpendicular, this is perpendicular, and as you can see, this angle is theta y, this angle is theta y, so this is going to be cosine theta y, cosine theta y, yes, theta x, theta x, theta x, you're right. Oops. So cosine theta x, cosine theta x, sine theta x, and sine theta x. So again, if you look at it, projection of new x1, y1, z1 on old x0, y0, z0. Please understand x1 and x0 are aligned. So one thing you remember, that whenever you have 1, all other columns and all other rows will have zeros. So if you have x0, x1, 1, columns are zeros, rows are zeros. Next, projection of y1 onto y0 is cosine theta x. Projection of y1 onto z0 is sine theta x. Projection of z1 on y0 is minus sine theta x. Projection of z1 on z0 is cosine theta x. And again, this transformation is 0 or 1, going from frame 0 on to frame 1. Everyone understood this? But at the end, I just want to, yeah.
I'm just gonna ask if the reason we only have to memorize the rotation for z, because we can express the rotation in y and x in the terms of z.
No. No, because that is how we are going to set up our coordinate system. And I don't want to remember 3 rotation matrices. Do you? No. Yeah.
Just for a sanity check, like can we say that for every rotation matrix the determinant will be 1?
Every rotation matrix determinant has to be 1, because every rotation matrix is an orthonormal matrix. Orthonormal matrix means all the rows are perpendicular. Of course, applied linear algebra. All the rows are perpendicular to all the columns. The determinant is 1. Example, if you find the determinant of that matrix, you will see that cosine square theta plus sine square theta, and then we are going to get minus. So basically, you will see the determinant is 1. And if you take the column, if you multiply if you find the dot product of that column with any other column or any other row, it's going to be 0. If you find the cross product, it would be 1. Dot product is perpendicular, so it has to be 0. Okay, any other questions? So once again, before I proceed any further, even if you don't remember rotation about y, rotation about x, everyone comfortable with rotation about z? Sine theta, so basically cosine theta minus sine theta, sine theta, cosine theta, and 1. There are 2 types of joints. So one is a revolute joint. So whenever you have a robot, an actual robot may look different, but for analysis purposes, you want to draw kinematic diagram. Kinematic diagram is sort of a sketch of the robot. How would the robot look? In this class, we are going to look at the robots that have 2 types of joints. One is a revolute joint, and the second one is a prismatic joint. So revolute joint is a hinge. So basically, there are 2 types of joints. Revolute joint and they are called R, and then prismatic joint. That is called as P. Now, a very simple example is if you look at the robot that I have drawn in the beginning of the class, you have a hinge joint here and you have a hinge joint here. So this is called as 2R robot. Now, if you were to look at, and I'm going to show you this 2R robot. If you look at the 3-dimensional representation of this robot is going to look something like this. So you have this revolute joint and you have other revolute joint. If you look this robot from the top, then you will see that this robot kind of looks like this robot. One thing I want you to understand, that this revolute joint is parallel to this revolute joint. Please note, this revolute joint, they are parallel. So this robot is called R parallel R. If you add one more joint, it would be R parallel R parallel R. Now, with that, what we are going to do is I'm going to try to work out few problems. First and foremost, given a robot, we need to draw the kinematic diagram. So if you see this robot, what I want to do is I want to draw a kinematic diagram. What is a kinematic diagram? Kinematic diagram is joint configuration, joint and link configuration in equilibrium position. So what does that mean? Is imagine you have the robot, and what I want to do is I want to represent the robot something like this. This is the first revolute joint, and what I have is I have this second revolute joint. So this is the first revolute joint, this is the second revolute joint. So this is like one hinge, you have a link, you have a horizontal link, and you have another hinge, then you have one link, vertical link, and one horizontal link. Think about it like you have two motors, and now this robot it's a cylindrical robot, so it has a configuration space, and it can actually trace the cylindrical path.
Yeah.
Everyone comfortable with this robot configuration? Two motors, which are parallel to each other. So this robot configuration is R parallel R. If you look from top, this robot is going to look like the robot that is shown over here. Now what I'm going to do is, and this is very important, and for next 1 month, we are going to do this again and again. We have to draw coordinate systems. Coordinate systems are extremely important. So what we want to do is, we want to draw the coordinate systems. So there are rules. So we have to follow these rules. Rules are, first, Zn axis is the joint axis. Now, what does that mean? I will explain one rule at a time. So can you see that this is the axis of rotation for the first joint? Do you agree with me? This is the axis of rotation for the second joint. I'm going to start with 0. So I will go 0, 1, 2, 3. 0, 1, 2, 3. So I'm going to call this Z0. So, and I'm going to call this Z1. This is going to be my 0th frame. This is going to be my first frame. So first frame. Then second is xn axis is perpendicular to Zn and Zn minus 1. This is extremely important. These are the same rules that you will use when you solve it by DH parameter. And I would explain this once again. This is the most important rule. Xn axis is nothing but the axis that pairs with Zn. This axis has to be perpendicular to Zn because it's part of the triad. Xn has to be perpendicular to Zn. But it's also important to note that Xn has to be perpendicular to Zn minus 1. What does that mean? Yeah. Now let's start step by step. Now, do I have, this is a very important question. Do I have Zn minus 1 frame? I don't. My frame starts with the 0th frame. So I have Z0. I do not have Z minus 1. Do you agree with me? So for the 0th frame, it does not matter. I would just draw my X0 wherever I want. I'm going to draw my X0 here. Why I am, so that you have a choice. Please understand. You can draw X0 like this, or you can draw X0 like this. Like this, like this. Does not matter. You agree with me? So I have just drawn X0 like this. Now, this needs to complete the triad. Remember, X, Y, Z. So now my Y has to go in. Are you with me this so far? Would be wise. And nobody has prevented us from X0 drawing in this direction, drawing in this direction, or even drawing in that direction. The reason for that is there is no coordinate frame before 0th frame. So we are okay with wherever x0 is. I have just drawn x0 in this direction. But since my x0 and z0 are fixed, I get y0. x0, z0, my y0 goes towards the board. Everyone understood this? Now comes the second part. Is I'll give you the rule number 3. Xn must intersect Zn and Zn minus 1. So this is the rule number 3. And the last rule is you have to use right hand coordinate system. So now please pay attention. These are the 4 rules. These are extremely important rules, whether you solve using DH parameter or whether you solve using rotation matrices. Zn axis is the joint axis. Xn axis has to be perpendicular to Zn and Zn minus 1. Xn must intersect Zn and Zn minus 1. And you have to use the right hand coordinate system. For the 0th frame, please understand that all 4 rules are satisfied. And the reason all 4 rules are satisfied because I do not have minus 1th frame. Okay. But now for Z1, let's look at the first frame. I need to find where my X1 is going to be. And I have multiple choices. So I'm going to show you the choices that I have. So I have 2 potential directions. I can use X1 in this direction, or I can use X1 in that direction. Do you agree with me? Now let's look at the rules. Xn has to be perpendicular to Zn and Zn minus 1. So Xn, can I draw Xn in this direction?
Yes.
Although we can, but we shouldn't.
We can, we shouldn't. Very good. And I want you to think about this problem a little bit. If you draw just for us and for the first part, I just want to show you. If you draw x1 here, okay, if you draw x1 here, please try to understand that x1 does not x1 intersects z1, but x1 does not intersect z0. Do you agree with me? Because they are parallel to each other. Are you able to visualize this? So the problem here is you have this, and then you have this, and then if you look at one coordinate frame, another coordinate frame, these x-axis, they are offsetted, they are parallel, they do not intersect. Everyone understood this? This is extremely important. So the only logical choice here is this x1. You agree with me? Yeah.
Can I take the direction of x1 in the negative?
This direction towards left hand side?
Yeah.
Yeah, absolutely. But let me tell you a trick. Whenever you are drawing the coordinate frame, if your next coordinate frame is in the same direction as previous coordinate frame, then you don't have to worry about the projection matrix. So if your x0 is in this direction, just for sake of simplicity, draw x1 in the same direction. I could have drawn z1 going down. That should not have been any problem. But since my z0 is going up, I'm drawing z1 going up.
Excuse me.
Yeah.
So can you repeat again how x1 is not intersecting with z0?
So right now, so which x1? The previous x1?
No, this is x1.
Now this x1,
The first frame.
this x1
Yeah.
is intersecting with z1,
Yeah.
right? And this x1 is intersecting with z0 because z0 goes infinitely up. Only thing is, if my x1 would have been in this direction, then this will go parallel to z0. Yeah.
These rules only apply to our parallel R configurations.
All configurations.
Well, how would we make x1 parallel to z1 and z0 if z0's going this way and z1 is going like this
Yes,
way?
we will look at those cases. Not yet. Hold your horses. Let's start with some simple cases. Yeah.
So in this case, x1 will not intersect z0 if there's a offset in the y direction.
Correct. But we will look at that case later. First, everyone understood this case? Okay, now I need to complete the triad. That triad is y1. And the last thing is, I need to set up, again, even though there is no joint, I'm going to set up a coordinate frame on the end effector. And the easiest way to set up a coordinate frame on the end effector is duplicate the coordinate frame that we have before. So this is going to be x2. This is going to be z2. And this is going to be y2. Now here comes the fun part. So now look at the joint rotations. I'm going to say theta 1 is the joint rotation here. Theta 2 is the joint rotation here. Because the first revolute joint, and remember, always the joint rotations are in the positive direction. So curl your fingers in the direction of rotation. Z0 and my thumb is pointing in the same direction. Curl your fingers in the direction of theta 2 rotation. Thumb is pointing in the direction of Z1. So please understand that theta 1 rotation is positive and theta 2 rotation is positive. Believe it or not, This is extremely important. But once you understand this, entire forward kinematics is done. I would explain this one more time. Whenever you have a robot, you would have to write the robot or draw the robot as combinations of revolute joints, prismatic joints, and links. The robot may have some weird shape, but at the end of the day, you need to represent that as combinations of revolute joints, links, and prismatic joints. So in this particular case, I have a two motor robot. I have a motor here, I have a motor here, and this motor is parallel to the first motor, and there are links. So I have drawn something called as the kinematic diagram. That is called as the kinematic diagram. Kinematic diagram should be drawn when all the thetas are zeros and the robot is fully extended. You cannot draw a kinematic diagram when the robot is folded onto itself. So you have one link, this is one revolute joint, you have other link, then you have the second revolute joint, and now what you have is, you have this robot. Everyone understood about the kinematic diagram? After drawing the kinematic diagram, you have to set up the coordinate system. For coordinate system, there are 4 rules. First rule is Zn is going to be the joint axis. And that joint axis for the revolute joint must go through the axis of revolution. Now, so you will have, second rule is Xn needs to be perpendicular to Zn and Zn minus 1. So Xn has to be perpendicular to Zn and Zn minus 1. And Xn must intersect Zn and Zn minus 1. So, and the last rule is you have to use the right hand coordinate system. Now, in this robot, first I'm going to draw Z0. I'm going to draw Z1. Once I have Z0, I draw X0. There is no frame before Z0, so I can draw X0 wherever I want. As a matter of fact, this Z0, instead of going up, can go down. But remember, Z0 cannot go in any other direction because the joint revolution axis has to be Z0. Next, I draw X0. Once I have Z0, once I have X0, I finish the right hand coordinate system triad. So now I have Y0. I go to the next frame. I draw Z1. Then I need to find where my X1 should be. X1 must be perpendicular to Z1. It's part of the triad. But X1 has to be perpendicular to Zn minus 1. That is only possible if my X1 is in this direction. And actually, my X1 could be in this direction. The only problem is, if I assume my X1 in this direction, it will not be intersecting with Z0. So it will violate the rules. So I would use X1, something like this. And then finish the triad. And the last but not least, I will actually put a frame at the end effector. Everyone understood this? Yeah.
So X0 and X1 parallel.
X0 and X1, they are parallel. Yes.
Then sir, how is it possible that X1 could intersect Z0?
X1 could intersect X1. Yeah. It's not offsetted. So basically, and Z0 is going up. Draw X1, it will intersect.
They're on the same
They're in the same plane.
So the offset, is visible from the top view, right, sir?
Okay, hold on a second. When you are drawing kinematic diagram, this is the configuration frame of 0th frame. This is the configuration of X1 frame. We are not rotating any frames. So when you are looking at this whole configuration, please understand, if your Z0 is going up, if your x1 can be extended towards left and right, your x1 would intersect with z0. Is there any confusion here? If there is confusion, ask me now. This is a very fundamental problem. Yes.
So even if x1 is rotated that way,
No rotation yet. Oh, I mean, right now in kinematic diagram, you are considering zero rotation. Value of theta 1 is 0. Value of theta 2 is 0.
So here we're assuming there's an offset only in the x direction, nothing in the y.
Yeah, there is nothing in y direction. There is only, yeah, you don't have a link, which is, and we will look at those cases. You don't have a link, something like this. So you don't have a motor which is here, and you don't have a motor which is over here.
So,
Yeah.
sir, when we would be performing experiments in the lab, for example, pick and place operations or any other permutation or combination with the robots. So all this learning would come into play over there.
Exactly. Everything what you learn here, you'll use in the lab. But we are not going to use a robot like this. It will be R perpendicular to R perpendicular R 6 times. We'll get there. Yes.
Which week do labs start?
It will start from next week.
Next week.
is the offset in the x direction or is it in the y direction?
Right now, the only offset is in this direction. There is no offset in y direction. Everything is in the x direction. Yeah.
Just insanity check, why not and why one are parallel, correct?
Yes, y0 and y1 are parallel.
Well, can you explain me again what do you mean by offset? Because the offset is in both directions, right?
No, offset is only in this. So I will give you the links. This is gonna be A1. This is gonna be A2. This is the offset. This is gonna be A2. This is gonna be A3. And it's gonna be A4. And since there is confusion about the offsets, I will draw a three-dimensional view. This is Z0, Z1, X0, Y0, X1, Y1, Z2, X2, Y2. Still, there is any confusion about which direction the offsets are? The offsets are, and I will give you these dimensions. A1, this distance is A2. This distance is A3. A3, and the last distance here is A4. Yeah,
These A2 and A4 are not the linked lengths, right?
these are the lengths of the links. Basically, these are the distances between the coordinate frames. Okay. Any question here?
Can we see the lab after?
Have you understood the kinematic diagram? Have you understood the rotation matrices?
Yes.
Okay. Because that is very important. And there goes my dream of finishing forward kinematics in one lecture. Anyways, so this is extremely important. Because what's going to happen is, one thing that I want you to remember, that all the rotations are about z axis. Can you see the rotation is about z axis? The rotation is about z axis, which means the only rotation matrix that is going to populate this guy would be the rotation about z. So that is the only rotation matrix that you should remember. What you should do is, if I have 5 more minutes, I'll finish it. But then actually, what you do is you formulate the rotation matrix, you get the projection matrix, find out the distances between the two frames, and that gives you your homogeneous transformation. You multiply the first homogeneous transformation by second homogeneous transformation, and you continue to do that, and your forward kinematics problem is solved. So in next class, I will finish forward kinematics. We'll work out 3-4 problems. But I would recommend that you review this material before coming to next class. I will discuss that in next class. It's wherein you will have rotation and translation.